Okay, so let's go back to our lecture. And on last Monday, right, we talking about that if we try to derive a special form of the momentum equation on the control volume, if the flow, okay, satisfy all these four assumptions, okay, if its flow is steady flow, there is no viscous force, and if the flow is moving along the streamline, and the density is constant, then we develop this special form of momentum equation for control volume, which is called the Bernoulli equation. Okay, so anytime when we talk about Bernoulli equation, okay, so you should automatically remember all these four assumptions that we made. And basically, this momentum, this Bernoulli equation, telling us that the pressure, this pressure, force plus the momentum, and plus the gravity force is called constant. Or in another way, if you want to looking from the energy point, okay, the pressure work plus the kinetic energy plus the potential energy is constant. Okay, so you can also think that this Bernoulli equation is kind of energy conservation format. Okay, although we derive this one from the momentum equation. Okay, and so let's just try to practice this equation. Okay, with some example problem. All right, so please read this problem first. All right, so for this problem, okay, we have a nozzle, okay, and so it's a one-dimensional flow, and the inlet and outlet, this nozzle, they have the different size of the in diameter, and for the inlet, right, we know what the volume flow rate will be, Q, okay, and this big Q is volume flow rate, and you should know that how we convert from the volume flow rate to the mass flow rate, right? You just need to times this Q with the density at the inlet. You will know what the mass flow rate will be. Okay, and so the question is asking that what is what the inlet gauge pressure, right? If we want this velocity, if we want this mass flow rate. So for this problem, okay, we are going to use this Bernoulli equation. All right, and the control volume, how we define this control volume is given on the picture, this blue dashed line here, and the this point location 1 is at the inlet, and location 2 is at the outlet. Okay, and so let's just try to calculate it, right? And so for the pressure, so if we look at each value, right, for the pressure at so for this inside this equation here, okay, we know that if we have this, how should I say? We also make an assumption, okay, significant and important assumption we made is that its density, we assume that they are constant, okay, they are not going to change, because that's why we can using this Bernoulli equation. And so if the density is constant, okay, and this desired mass flow rate is known, okay, so we can immediately calculate that, we can immediately calculate that what the velocity correlations between the inlet and outlet from the mass conservation, okay, because that your velocity times density, okay, and times this surface area, this cross-sectional area at the inlet will be equal to the density times your velocity and times cross-sectional area at the outlet. So this is not, so we also have a conservation of the mass we can use here, okay. And so what I want to say is that what I'm going to see. So let's go to here directly, okay. And if we, for the pressure, okay, at the inlet we do not know, and for the pressure at the outlet we already know it's 1 atm. So for the pressure at the inlet, we can write that this gauge pressure here, all right. And so we can know that the gauge pressure at the inlet is equal to P1 minus atmospheric pressure, okay. And we know that this atmospheric pressure will just equal to P2, right? So basically it's P1G. The gauge pressure at the inlet will equal to P1 minus P2 because P2 equal to atmospheric pressure. And this P1 minus P2 can be directly given from this Bernoulli equation, okay? Because that you just need to move this P2 to the left and move everything to the right, okay? So that's why that this P1 minus P2 will be equal to this value. And this value we get from the Bernoulli equation. And it's here, because that the flow is moving horizontally, okay? So this is Z1 and Z2, they are the same value, so they cancel. So the only thing left is this V1 and V2, all right? So basically your gauge pressure will be as a function of the density and velocity be given as this way, all right? And also because the continuity equation, okay? From the continuity equation, we can know that this V1 times A1 will equal to V2 times A2. All right, and so the ratio here is V2 over V1. This is the velocity at the outlet over the velocity at the inlet will be just equal to the inverse ratio of the cross-sectional area. So it will be equal to A1 over A2. Yeah, and also knowing that this V1 value is given by Q divided by A1. Okay, the Q is the volume flow rate, and divided, so this V velocity times the cross-sectional area will give you volume flow rate. And so you just substitute these two equations to here, and you can get that what this gauge pressure will looks like as a function of Q, and also that you just remove all the velocity terms and only related to the area terms, and so you get this result here, okay. And also that we know the D1 and D2, right? We know the diameter for the inlet and outlet, so we can know what the area for the inlet and outlet. So you just substitute this diameter for replace this the area terms with this diameter value. You can get this final result here. And here is so this is a correlation we get here, and for if we know the density is 1,000 kilogram per meter per cubic meter, so this is the water density, and you just substitute that all the value here we have the to into this equation here, and also that this Q dot value is not known yet. Okay, so just substitute all the known value into this equation, so we can get this final result. Okay, correlation with this gauge pressure as a function of the Q. Okay, as a function of your of the volume flow rate, and with this target Q, if we using this target Q value 0.02, so we can calculate what the gauge pressure will be, and you add the 1 atmospheric pressure to this gauge pressure, you get the you can get the absolute pressure at the inlet. Okay, and so this is just how we're using this Bernoulli equation to calculate this problem. So for this problem, actually, if you do not want to use the Bernoulli equation, you can still using the original momentum equation to calculate it. Okay, you will get the same result. But from here, you can see that the Bernoulli equation is much simpler to do the calculation. And so the whole idea here, okay, is that from this Bernoulli equation, we can get the correlation between the pressure of other terms, okay, and we also using the mass flow rate, we're also using the continuity equation to relate the velocity and that area, okay, and the density. The density, where is mentioned that this density value? Okay, it says the water. Okay, that's the reason we know the density value. Okay. So for this problem, it's It's what we did here. Okay. All right. So for this problem, that's that we try to calculate the pressure here, right? From this Bernoulli equation, we calculate the P1 from the Bernoulli equation, and we do not know the V1, we do not know the V2, okay? But we do know the P2, and we know the rho, okay? So if we want to use this Bernoulli equation, we want to calculate the P1 because this is the pressure we want to get. The only thing we do not know is the P1, V1, and V2. But the good thing is that this V1 and V2, okay, can be given by two things. One is this continuity equation. From the continuity equation, we know that this V2, V1, okay, the only one of them is independent. And the second thing is that we know this mass flow rate Q dot. And from the Q dot, we can know in one of the V1. Okay. And that's it. So this is the inlet, the desired flow rate at the inlet. I think for this problem, desired flow rate. Okay, so inlet to produce a given volume flow rate. All right, yeah. So this Q, you need to know that this Q is at the inlet. Okay. So I don't think it's read very clearly. So this Q is for the inlet volume flow rate. That's it. Okay, so this is how we can practice this Bernoulli equation. All right, so the next concept we are going to talk about that is that remember that the momentum equation, right? We derived is based on the Newton's second law, and the Newton's second law is only valid for the initial frame, right? So which means that the momentum equation, you know that the momentum equation we derived before for the control volume, and also this special form Bernoulli equation, all this equation, okay. What I want to say is that this equation here, this equation here, this momentum equation we derived for the control volume, and this component form, and also that special case that this Bernoulli equation, when you have that for assumption valid, all these momentum equations, they are only valid for the initial frame. Okay, and so let's talking about that some other a special case that if your control volume is moving with a constant velocity, so which means that now if we assume that we have two. Professor. Yes.
If it's moving at a constant velocity, isn't that the definition of an inertial frame is something at rest or moving at a constant velocity? Meaning.
Yeah. Let me continue. Okay, I will go there. Don't worry.
Okay.
Yeah. So for this problem, let's assume that we have two coordinate system, right? One you have this big X, big Y, and big Z. So they are fixed there, so they are not moving. And also you assume that you have a new coordinate system which is X, Y, and Z, small x, y, z. Okay. And this coordinate, okay, they are moving with a constant velocity u here, okay, or we can write a v of RF, okay. I think we can write this as v of RF with a vector, okay. This RF means the reference, okay. So which means that this is the velocity of this reference frame over this stationary frame, and now they are moving with a constant velocity. Moving a constant velocity means that this new control volume, this is a small x, y, z, this coordinate system, okay, this reference frame, because it's constant velocity, so they are still an initial frame, okay. So which means that the Newton's second law is still working. And if all the value, okay, if the value, if we want to using those velocity value, okay, and the force value we measure inside this moving, this new moving reference frame, rather than using the value we have before for this stationary frame. So what's the control, what's the momentum equation looks like inside this new frame, reference frame, small x, y, z. Okay, I can tell you what the result will be. Okay, the result is still same as before. Okay, so you can have no additional term here. Okay, it will be the same equation, and the only difference is that this v of x, y, z here inside this equation, and this v of x, y, z here. Now instead of using the instead of using this original v of big xyz, okay, we just replace that this small v of small xyz. We have this correlation here, okay, and which means that you know, any particle, okay, any atom, any fluid, okay, moving inside this moving, okay, their velocity in this moving, their velocity in this stationary reference framework will be just equal to the velocity of this fluid particle moving in this moving with this new, okay, reference frame plus this r v of rf, and this v rf is this constant velocity of this small xyz frame, reference frame moving corresponding to this big xyz frame. Okay, so we have this correlation here, and so if you substitute this big v of xyz into our original correlation before, do I have it? Where is it? So here, okay. So you substitute that big v of xyz, okay. So you just replace this one with this, you know, v of big xyz will be equal to this small v xyz plus this v of rf. You substitute this one into here. You substitute this equation into here, okay. And so what do you get? Because that this is a constant value, okay, and then you do partial t of this constant value, so this is gone, okay, this value will be gone. So the only thing that will be this small v of xyz here directly instead of this b v xyz will be, right? And for the second term, for this flow, this is a net flow. This is a net flux, right? Net flow momentum flux around the surface, right? And so for the net flux, okay, net flow flux around the surface, right? Maybe using this equation as an example is more easy to understand using this special case, sigma cases, okay? So which means that you know, the flow in minus flow out will be this one, the momentum flow in and then flow out. So their absolute value is not important. Okay, the important thing is that if you have flow, okay, you have the inlet and you have outlet. Okay, inlet outlet, and the difference between inlet and this outlet will be more important. So for example, for these cases that so the flow moving in will be this u inlet, right, times this rho times this. So you have 2u here. Let me rewrite it. So I want this. So let me give you the thing. So what I want to see is that for this term, okay, this integration term, the important thing is that what the net value will be. And so if we have here, so what is moving in and what is moving out, right? Let's assume that you have this u of I as in and u of e as out. So basically that should be ui square times ai times this rho minus u of e square times a of e times rho, right? This is a value, it's important, and also that because that this mass conservation, right? Because that we also have mass conservation here, so we know that this u times a times rho equal to mass, right? So you can also write this just as ui times m dot minus this ue times this m dot. So the important thing is this ui minus ue. Okay, so you can write this as ui minus ue times this m dot. So this is what the net for flux, momentum flux for this problem. And if you just change the reference frame, and you just give this ui and additional u this rf reference frame constant reference velocity, and give this ue a constant reference velocity, it won't change that the difference between these two. Okay, so in another word, okay, if you just substitute this v of xyz, okay, equal to this v of small xyz plus this v of rf, you substitute this one into this equation. All the terms regarding to this VRF, after you do this surface integration, they will go. Now, of course, you also need to combine with this mass conservation, okay? So what I want to say is that if you substitute this correlation into here, you can directly get the result. What the result will be? Not here. If you calculate it out, so that's why is that if we try to move our reference frame from a stationary one to a new one with a constant velocity, okay, to a new frame with constant velocity, it won't change any of your format of your momentum equation. No, because that two things, okay. The first thing is that it's still initial frame because it's constant velocity, so that the Newton's second law is still working. The second thing is that you know that difference because that the difference between the velocity difference between the new frame and with the old frame is a constant value. And if you substitute this equation into the original equation, okay, into the stationary the momentum equation for this stationary velocity, the momentum equation for this stationary reference frame. So final result will just equal to this one, okay. So in the end, okay, it's just telling us that if you have a reference frame, it's moving with a constant velocity, you just keep the same format of your momentum equation. That's it, okay. So has the same form comparing to the momentum equation for the xyz coordinate. The only difference is that the velocity you use the inside. Now this velocity is a reference to the new framework. Okay, not to reference to the older reference framework. Okay, and this is a control volume moving with a constant velocity. Yeah, and let's also do an example problem for this problem here. Okay, so for this one, okay, and the water will coming out from the nozzle and heat this vane here, okay, and this vane will change the direction of this water, which means that you change the momentum, and that's why that there is a force will act on this vane here, and we already know that this it will move with a constant velocity v equal to 30 meters per second, so which means that this vane will move with a constant velocity. And when we define the control volume, right, because we want to find the force act on this vane, all right. So we just, when we do the control volume, we make this to include all the vane region, okay. And the special thing is that if we define this control volume attached to this vane, because this vane is moving with a constant velocity, so which means that this control volume itself is also moving with a constant velocity. All right, so that this go back to our the problem we just the equation we just derived earlier, right? So if a control volume, okay, is moving with a constant velocity, their momentum equation will not be changed format, okay? And this is the momentum equation, all right? And remember here now we change this in this momentum equation we have this v velocity. Now this v velocity in this momentum equation is relative to this new moving framework, okay? Which means that we define a new framework like we have this this is x, this is y, okay? Let's assume that this new framework xyz is attached to this vane, Okay. So when we want to get the force, so the force is coming from the momentum equation, all right? And so we just try to calculate the two components, the x component and the y component for this control volume. And on the x component of the momentum for the control volume, F of Sx is the surface force plus the body force. On the x direction, we do not have any body force, okay? Because the only body force is this weight and supporting force from the ground, and it's all of them at the y direction. So the body force on x direction is equal to 0, and it's a steady state problem. Okay, so that this partial t term is equal to 0. So in the end, okay, telling us that okay, this x direction force, which is this resultant force on x direction, we want to looking at value. This is the x direction force act on that wing, will be just equal to change of this, the surface flux, momentum, surface momentum flux, okay, on the x direction. And so we just substitute the things here, and we have two parts, right? One location is this inlet location, and another location is this outlet location, okay. And so if we do this integration on the two parts, and let's also assume that the velocity distribution on this inlet and outlet is uniform, so we can directly write that this will be equal to this u1 minus rho v1 a1 plus this u2 times this rho v2 a2, okay. And this v here is this big V is the velocity leaving to this nozzle, okay. And and you see that you also have the same okay. So we have this V1 and V2 here. Is that the relative this V1 is the fluid velocity at the inlet, and V2 is the fluid velocity at the outlet. And this U1 and U2, okay. U1 and U2, what's this U value will be? U value is the so U1 value is that the x direction component of the V1, okay, and U2 is the x direction component of this V2, okay. So this U1 and U2, U1 is the x component for this V1, and U2 is for x component for the V2, okay. And remember that when we define this control volume, right? Now with this moving frame, right? And so the V1, U1, V2, U2, this is at the velocity we measured in this moving reference frame. Okay, so in the other word, so if we have the so if, for example, if we have this this big V and this big V is this big, I think they drawing this as a typo here. This is should be U, okay, not V. Okay, this big U, okay, is oh no, is V. Okay, make mistake here. So this big V is the velocity of the fluid, right, at the stationary frame. This large xy, okay, and this big U is the movement of this reference frame will be, okay. So V1 here will be just equal to this big V minus U, because this V1 is just the fluid velocity at the inlet, okay, to reference to the new coordinate system. And also that this V2 will be this V2 here, okay, the outlet velocity. First, okay, let's calculate the V2 here. Okay, we can calculate the V2 through this mass conservation. Okay, because that the mass conservation, the summation of your inlet mass flow and outlet mass flow should be equal to 0. Okay, because that is the conservation of the mass, and you have this correlation here. And because that A1 A2 is the same, okay, we assume that A1 and A2 is same. We assume that we have the same, this film of the fluid has the same thing as location 1 and location 2. Okay, we assume that V1 and V2 is the same, and sorry, A1 and A2 is the same and the same density. So we know that v1 and v2 is same. Okay, so which means that the speed, okay, the magnitude of velocity at the location 2 is still is same the magnitude of velocity at the location 1, but the direction is changing, but the magnitude is same. And so that's why that in the v2, okay, the reference the new velocity v2, okay, at the outlet will be just equal to v minus u, okay. This is for the new coordinate system. And u1 is the x component of this one, u2 is the x component of this one. So that's why that u1 equal to this value, and u2 will be this value times cosine theta. This theta is 60 degree. You have 60 degree here. Okay, x component this one, and you substitute these things back to the to the x direction momentum equation here, back to this equation here. Okay, and since v value you know, u value you know all the velocity, and you can calculate what the x direction resultant force will be. Will be minus 599 Newton. Okay, so that means that basically we need to have a force. Okay, we need to have a force on this direction, go to left, to make this wing moving with a constant velocity. So if we didn't provide this force, okay, Rx on going left, then this wing won't able to keep this constant velocity movement. This constant velocity movement is that will be accelerated actually. Okay, so that is Rx. And what's the y direction force? The y direction force is much more simpler. Okay, the y direction force is also using this y component of the momentum. Okay, and the body force now it will be the body force now will be the we can be the weight of this wing. Okay, so your Ry minus this weight of wing will be the change of the velocity momentum on the y direction. Okay, and the momentum on the y direction will be just equal to the v2 times the rho v2a2. So this is the y direction momentum at the outlet. Okay, and then I think there should be there's a typo on the book. This should be -1 minus, and this should be 1. Okay, so and then minus that what's the y momentum on the x direction, and this will go to 0 because that on the inlet we do not have y direction momentum. We only have the y direction momentum at the outlet, and the y direction momentum on the outlet will be just the momentum times this cosine theta, so as cosine 60 degree. Okay. This sine cosine. Times sine theta, sine 60 degree. And so this is the change of the momentum on the y direction, and you get the resultant force. Okay, and you know that this will be the value. Okay, so this is an example problem, right? So if you define a control volume in a reference of frame which is moving with a constant velocity. Okay, so the idea is that you're using the same format of the momentum equation, but you can directly change the outer velocity inside to be the relative velocity rather than the absolute velocity. Okay, the relative velocity is the velocity regarding to this moving coordinate. Okay, so this is the whole idea here. And so this is the cases that we finished the cases that talking about the momentum equation for the initial frames, right? Those when the control volume is moving with the constant velocity, they are still the initial frame. And what happens if we are try to derive the momentum equation in a non-initial frame, such as that a special case we are mentioning here is that it's if you have this small xyz frame, right? If they are moving not with the constant velocity anymore, but moving with constant acceleration, a constant rectilinear acceleration, not a rotation acceleration, okay? Not just a rectilinear acceleration. So what will going to happen? All right, and so in these cases we just need to so in these cases, okay, we just need to starting from the system, because that for this system we still you know, what should I say here? Because for the system, if you look at this system is followed by this math, okay, this system itself, okay, and their framework is still, their Newton's second law can still working. And so if we started from the system, okay, so because we still define two coordinate system. This big xyz is the stationary one. So in other words, this big xyz is still the initial frame, and that small xyz is moving with a constant rectilinear velocity. So this is not the initial frame anymore. So let's take a look at the Newton's second law in this big xyz, because this big xyz frame is still initial frame. So the Newton's second law is still working. So F equal to dp at xy or dt. This p is the linear momentum, all right? And so you can write on this one. And this big V of xyz is the velocity regarding to this stationary reference frame. And we know that this correlation here, okay, and the velocity in the moving frame, okay, plus the velocity of the reference frame itself will be just equal to the absolute velocity in the stationary frame, okay. And if you do the time derivative on this equation, okay, and you get this correlation here, and so this is so get this a of b xyz, which means that the acceleration value regarding to the stationary frame will be just equal to acceleration value regarding to the moving frame plus the acceleration of the reference framework itself. Okay, now you substitute this correlation here into this equation to replace this d big V xyz over dt here. You can get this equation. Okay, it's telling us what? It's telling us that the force will be equal to the, you know, the change of the momentum inside this moving coordinate itself, and plus the change of the momentum of this coordinate system itself. Okay, so this A of RF is the change of the momentum of this reference frame system, and this is the change of the momentum for the fluid inside this reference frame, moving reference frame. You have an additional, so you can see that by this way, okay, we have our Newton's second law here for this system, we have an additional term. All right, so we can rearrange it. So we can write in this way here. Okay, and now, okay, remember that so we can rearrange it in this way, and this pxyz, this is a linear momentum, okay, in this new, okay, small xyz reference framework, and it can be given by this one, small v xyz times dv, and also so that from this one we can know that the change dt of this one can be written in this form. Okay, so this is okay, this is the correlation, okay, that you know, different derivative correlation between the system and the control volume, right? That is correlation we had before. Okay, we got it here, and you substitute this value, okay, into here. Okay, and you can get the final result. Okay, so if you are confusing with how we derive everything here, it's fine. Okay, it's not very important that you know how to derive this, but the important things you need to know is that if you have if your coordinate system, okay, is not a initial frame, is a non-initial coordinate system, your momentum equation will have some additional terms here. Okay, if you're looking at this equation, comparing to the momentum equation we had before, either that either that this system is stationary or this coordinate system is moving with a constant velocity. Okay, you will see that this is the only additional term here. Okay, and this two term is still same as before. You have this change of the momentum, okay, on the inside the control volume itself, and this is a net momentum flux across the whole control surface. And we have this surface force, we have this body force, but we have an additional term. And this addition term, if we moving it to the left-hand side of the equation, you can think that this addition term is like some, fixtures or artificial force. Okay, and you can think that okay, it's like if it's it's not moving with if you're using a reference framework, okay, it's not a initial framework. Okay, you will have some additional, fixtures force need to be included inside of this momentum equation. And for these cases, if this is moving with a rectilinear acceleration, so this fixture force will be this rectilinear acceleration times this rho v. Okay, and so this is so this is a times the because this is integration on the control volume, right? So this is the acceleration times the mass. This is ma, right? So this you can think that this is the fixture force is coming from this this framework acceleration itself. Okay, so this is the important thing you need to know. All right, so this is the equation you have for you have the control volume non initial frame. Okay, for this control volume, if they are moving, this reference framework is moving with the rectilinear acceleration constant. Okay, and you can also write this equation in the 3-component form on x, y, z. Okay, and on each component form, on each component direction, you have their own this new term. Okay, for it. So this is the momentum equation. What the momentum equation looks like. Okay, if you have the control volume has a rectilinear acceleration, right? So just remember you will have these new terms here. So we will have another example problem for this one. It's similar problem as before, but now, okay, this wing, okay, is not moving with constant velocity. Okay, it can move with arbitrary acceleration. Okay, and I will go through this example problem next week. All right, not next week, on Friday. And but before I finish, I also want to let you know, okay, there is also things, okay, that if let me also give you another example, because this is not included in is out of the context of this class, okay. But what if you have a reference framework, this small xyz, okay, is moving with arbitrary acceleration, like to assume that the moving with acceleration, rectilinear acceleration, also moving with also has their own rotation itself. Okay, let's assume that this reference framework has 2 acceleration. One is the rectilinear acceleration, which is this a of RF, and also that this xyz also rotated with a fixed axis with this rotation velocity omega. So what will be, okay? So this this will be what the momentum equation will looks like. Okay, now you can see that this is still same as before. This is still as same as well. These 2 terms still as same before. But this term, which I see that this is called the fixtures, okay? Fixtures force due to this non-initial frame. Okay, now it become more complicated. This is still that acceleration force before, rectilinear acceleration force due to this reference framework. And this one, okay, is called the Coriolis force. And this force is centripetal force because this rotation. And this force is the tangent force because of rotation. Okay, so this 3 force, you will have another 3 force here. This is 3 force because this is rotation of this framework itself. This is Coriolis, okay, Coriolis force. So this is centripetal, and this is tangential force due to this rotation. All right, but this is not this is just for you to knowing that if this momentum equation, okay, if we try to define it in a non-initial frame, okay. So basically, we need to on the left-hand side, we need to include in this fixture forces, okay, due to this non-initial behavior of the framework itself. All right, so I will just stop it here, and I will see you on Friday. All right, and the last thing, okay, I also assigned a new homework for this chapter 4. Okay, You can find it on the blackboard. So it's still assigned through the YD plus. 10 problems for this chapter 4. All right, now you should be able to answer the first 8 problems, and after the next class you should be answer the other 2 problems. Okay, and it's a lot of problems, so I give you 2 weeks to finish. Okay, so do not wait to the last week because there is really a lot of problem there. All right.
Professor?
Yes.
It said that the homework was due today on Wiley, but on Blackboard it says it's due the 26th.
26th, Theo.
No, but on Blackboard, if you go to Wiley.
Oh, okay, I'll fix it. Okay.
Okay, thank you.
No problem. I'll fix it. All right. So there's no question. I will see you guys on Friday. Okay. Bye, everyone.
Thank you.
Bye.
Bye, Professor.